I would like to go today, start today, from a result that we left yesterday. Left it unfinished up. I just overlooked it. I would like to do it more precisely. Okay. And this was about, this is was about how to create new martingales. This result was that how to create new martingales. In other words, if you have a predictable process and a martingale, you can create a new martingale out of it. Okay. And that martingale is roughly going to be what we call the discrete stochastic of that predictable process with respect to the martingale. So let me state it precisely. So if I have a martingale and a martingale with respect to obviously filtration, and H be predictable process. In a predictable process, that each HN is okay, is measurable with respect to filtration at the time minus 1. So for adaptiveness, we say that each process at the nth time is measurable with respect to the filtration at the nth time. But by predictable means that you can predict the process. The process is measurable at the time. Process at the time n is measurable at the time. Obviously, it's going to also be measurable at time n. Fn minus 1 is a subset of included in it. These are the basic conditions. And then we said that if M and H additionally satisfies one of the following conditions, if this M H satisfies one of the following was one of that's important that H is bounded. Okay, is that I can find a positive number k such that the absolute tension is less than or equal to k for all n. Second condition, not second, but the alternate condition is that if H and M both are square integral, H and M are both square integrable, or H is bounded and M is just martingale, then using this martingale in a predictable process, what you can do, you can define another martingale. This new martingale is going to be roughly, if you look at it, I denote it by the following process is a martingale. Okay, martingale, but with respect to the same filtration to which this guy is the martingale.
Sir, दोनों HN one filtration होगी.
HM yes. When I'm saying that when I'm defining predictability, I'm defining it in the terms of
Sorry.
In other words, if a filtration is not explicitly mentioned in the theorem, that means that you are talking about the same kind of filtration. Okay. Following process is the martingale. The process is that xn is basically j is equal to 1 to n of hj multiplied by the increment of the martingale.
Subscripts.
Not, okay. Right. Scripts, right. And X naught is the now. I mean, if you see, you can kind of roughly interpret that this process xn is basically the discrete integral of the predictable process with respect to this martingale. Okay? So in other words, this is discrete integral becomes this guy become this guy, and now that this is a kind of a discrete stochastic integral. So it's proof goes. We have to, for example, go. What would be y xn is the first thing that you would like to do is that xn, the absolute of xn is finite. Okay, finite. We are most sure. We have to keep that here almost all of the inequalities that you're gonna do between do about the expectations. It's going to be almost true. I'm not mentioning it, it's there. So why this should be true? So I need to do what? That's the first property that the martingale should satisfy. It must be integrable. So I need to compute the absolute. If I compute the absolute of computing the absolute of this guy is same as computing the absolute of this guy. And if I, for example, apply the triangle inequality, okay, we have j equal to 1 to n, absolute of hj times absolute of mj, and mj minus 1. Okay? This guy is, like, let's estimate this by number k. You can take the expectation as well. Okay. So we see as that we have this j equal to 1 to n, and the expectation of the absolute of mj and mj minus 1. So using the linearity and now, since mn is a martingale, its increment should also be martingale, or I can say that the difference can be estimated by the individual sum of mj minus 1 and then take the expectation. So if we take the expectation, okay, of absolute of mj plus, say, absolute of mj minus 1, since m is a martingale, these two guys are going to be finite for every j. For sure, this is finite. Measurability, in other words, why xn is adapted to. The second thing that we need to think about is that xn is adapted to this underlying filtration process. Why you have this adaptiveness? Think about it. if I write, say, for example, xn more explicitly, you can see it very immediately. H1 minus M1, so on and so forth, and the final term is going to be Hn, Mn minus M minus 1. Now, can we argue that this expression is measurable? Now, H1 is predictable. Okay? So it's measurable with respect to what? With respect to F naught. Okay?
So
Hence F1.
So it would be H1 times M1 minus M naught.
Yeah. So
Yes, so subscript M1 minus M naught.
okay, M1 minus M0. Okay. So I'm saying that clearly this guy is F1 measurable. Okay. And since it's F1 measurable and F1 is included in Fn, so it is also Fn measurable.
Second,
I can argue similarly about this that this is Fn measurable. So Fn measurability, in other words, this is measurable with respect to the signal field. So you can't just see, obviously, but you have to look at it and then figure it out. Okay. That's the second property. The key property is, what do you see? The martingale property. So what I need to do, I need to compute the expectation of this process, discrete stochastic integral at time n plus 1 given Fn. Okay. I need to show that it must be same as Xn, we are almost sure. So what would be this? So if I write it explicitly, it is something that starts from, for example, H1, just to show you it, how it goes. Okay? M0 plus Hn, Mn minus 1 plus final term is going to be Hn plus 1 and Mn plus 1 minus Mn and everything given as that. Okay. Now, all this expression, so I can apply the linearity property of expectation and so on and so forth. Okay. This expression is Fn measurable. Already saw it. Okay. Up to this point, this is Fn measurable. So in other words, that this guy is going to come out as it is, out of the expectation actually. Okay. So what is called taking out what is known. So applying expectation individually using linearity property and then applying taking out what is known property, you can get what sum from j equal to 1 to n Hj n
Mj minus M.
Mj minus Mj minus 1.
Expectation of one that is.
How about this one now? Now, since h is predictable, so this is measurable here, so okay, plus right. So Hn plus 1 is measurable, so I can pull it out of expectation, using taking out what is known. The only thing that is going to remain is now this expectation of Mn plus 1 minus expectation of Mn
Given different.
and given Fn. Okay. My expectation of Mn plus 1 is going to be what? So I can apply linearity. So expectation of Mn plus 1 is going to be Mn.
Tuesday martingale.
It's a martingale. And Mn is measurable here. So it's going to be equal to Mn. So this would be 0. Okay, this would be 0. Because the both expressions are going to give you Mn and hence they'll cancel out. And what is this guy? This is nothing but the vector. And that's what you wanted to show. Okay. That's what you wanted to show. Okay.
Why this guy goes to 0, sir, again?
Sorry?
Why this guy goes to 0?
Because apply the conditional expectation individually on this. So expectation of Mn plus 1 given Fn is going to be Mn. And the second expression is going to be expectation of Mn given Fn.
So if Mn is measurable, so
Immeasurable, so you know. Okay. So we saw that under the assumption that H is bounded, you know, this discrete stochastic integral becomes a martingale. For the second assumption, think for yourself. I think this would not change, this would stay same. The only thing is going to be the proof of
integral.
this integrability. You can already see that why you need, you know, square integrability. Think about it. Why? What do you think? Why you need square integrability here? So, when I had a boundedness, so I can estimate Hj by k. So I remember this, for which I know that the expectation is fine. But imagine that I don't know the boundedness, I know that what's the called square integrability of the both what we call possible. So what we can do, think for yourself. Think for yourself. I don't think it's not that difficult. You just have to use an inequality and that's it.
Coefficient.
Apply the coefficient. That's what you have to do.
And two measure.
Both are going to expectation of Hj square, expectation of square. We need both finiteness. Anyway, okay. So what's a beautiful thing about this theorem is that it allows you to create new integrals, you know, new martingales out of existing martingales by using a predictable process. And this is going to be something interesting. We're going to generalize this to the continuous time case as well. Okay, they are going to be very interesting. And why we want to meet is something that we discussed. You can also read what you call a small, for example, a paragraph here which talks about that why martingales are interesting. They are interesting because if you involve them in finance, they turn things into, what you call, they allow you to do the fair pricing, okay, where there is no arbitrage. And exercise 1.8, okay, it's a difficult, it's a bit tricky exercise. Okay. I will not suggest that you spend too much time on it. You can, if you wish. Please, I'll send you the solution, you can have a look on it. But exercise 1.8 talks about the converse of this action. Okay. In other words, if you have okay, so if I have a predictable process, then I can construct a martingale in this form. Okay. The converse is that if you have a martingale, then you construct a predictable process. So of it's a converse of following theorem is supposed to that. Okay. So I would like to move towards the next thing that you can obviously, so one of the property that we saw about the martingales is just that, if you make it, so if you have two martingales, then if you make their linear combination, the linear combination is also going to be a martingale. But you can ask immediately a question how the higher order powers. Is it possible that the powers of a martingale is also a martingale? And the answer also comes from an exercise. Okay. And that's what we have to do. This is exercise, I guess, 1.9, which says that if you have Zn, that is symmetric random walk, okay, symmetric random walk, and then you try to prove, for example, the martingale property for the square of this symmetric random walk. In other words, if I try to compute, for example, that the square of n plus 1 given Fn, okay, Fn is the sigma field generated by the symmetric random walk, then you will, the good thing is that you will get Zn square, but you also get a 1. Okay. So what does this show? This shows that the square of the symmetric random walk is not a martingale. The square of a symmetric random walk is not a martingale.
सर ये जो हम मन हमें मिल रहा है ये जो LJs थे जिसमें हम LJ is equals to 1 कर रहे थे
That's what you have to prove. I know how to do it. That's what is your job to do. You have to try to figure it out. But at least what does this show is that, I mean, if we didn't have this, then it becomes. You expect it to be a martingale, but you have a plus 1, so no chance. Okay? No chance. So symmetric random walk is just one kind of an example. What we can show, and I'm going to show basically using the Jansen's inequality, that if you have an abstract martingale, you can't have such equality. In fact, you're going to have inequality actually. Okay? You're going to have inequality. So you remember Jansen's inequality? Jansen's inequality tells you that if phi is a convex function, okay, it's a real valued convex function. Okay. Then the expectation of phi of x given sigma field, okay, can be estimated by phi of the expectation of x given sigma field. That's what is essentially that. Then, yes, that's in the ring. Does it make sense? That's what it is. So let's use it on a square of an arbitrary, what do you call, martingale.
So in the last bit is phi of expected of x.
Yes.
5x given this.
The phi of the expectation. Now, take phi of x to be, let's say, x square, which is convex, you compute its second order derivative. Turns out to be always one negative. Okay. Positive, so it's convex. Saying that, okay, take now, say x to be, say a martingale, the process martingale evaluated at the time n plus 1 actually. What you're going to get if you have this? You're going to get an expectation of n plus 1 squared given, say, Fn. Let's try it. So have Imagine you have an abstract martingale. Okay. An abstract martingale. And I want to see that whether its square is a martingale or not. Okay. I have some hint that okay, symmetric random walk shows that it's not a martingale. Can we have something like this here? So expectation of mn square, so it would be, I can estimate this by less than or equal to
The square of
summation of
all is
plus 1 and it's square. No chance. No chance. What would be this, for example, if this is martingale, this would be equal to not having equality. Using the martingale properties. So what does this show? Is it going to be greater than or equal to? Right in. Okay, so okay. Writing a wrong version of it. So greater than or equal to, not the less than or equal. So square of martingale is not a martingale, but it's something else which I'm defining in the book.
and it was a
ये और ये ठीक है ठीक है नहीं So what does this show? That obviously square of an abstract martingale is not a zone. So martingale roughly allows you, to model the fair game. Playing time crossing game, we know that it's going to turn out to be so for example, symmetric random walk, which is a martingale. So it allows you to model the fair game. The next question that you can ask, can we model the unfair games? In other words, the game which is going in the favor of any one of the, for example, participants actually, going in my favor, going against my favor actually. Okay? So if the game is going in my favor, what do you think what should happen after? Imagine you have gains. I know that gains can be treated as a martingale, like make a symmetric random walk out of it. Turns out to be a martingale. And I'm saying, so if my gains are martingale, then I know that the expected value of the game doesn't change. It always stays same. So if the game is in my favor, what will happen? So as time progresses, the expectation should increase actually. Expectation of my gains should go more and more and more. And if the game is against me, expectation should go down actually. Goes against me. Can you have a process for which such kind of what do you say? Such kind of behavior actually? Answer yes. Okay. The next thing that we'd like to define is sub and supermarket. Okay. Here's the definition. So I have a process xn. Stochastic process. Stochastic process. Such that just like it in words, such that it is adapted filtration. Fn and diagonal. These are the two properties it has. Satisfies these two conditions agree with martingale. Okay. Then this process is called submartingale.